Alright, so in this video I'm going to show how to derive the prediction interval for a new response. And we've already discussed how to do this, but in this video I'm going to show how to do it using matrix notation. Alright, so recall our model when we write it using matrix notation is y equals x beta plus epsilon, where epsilon is our model error and it's normally distributed with mean 0 and variance sigma squared times I. Okay, and just to be clear here about our dimensions, y is n by 1, so it's the vector of all of our outcomes. X, if this is a simple linear regression model where all I have is an intercept and a slope, so only one value of x, then this would be an n by 2 matrix. And beta would be the beta naught and beta 1, right? The intercept and the slope. So that's a 2 by 1 vector. And epsilon is an n by 1 vector. Okay, so we're talking about a prediction interval for a new response, y naught, right? So y naught is not observed. Right, and it's just 1, it's a scalar, okay? So this is just a 1 by 1 scalar, okay? So what is y naught? Y naught equals x naught, right, and times beta plus epsilon. So x naught is a 1 by 2, okay? And beta is a 2 by 1, and epsilon is also just a scalar, a 1 by 1. All right, so x naught, it's a 1 by 2. What does that mean? So this is like, for example, so first column is always 1s, right? That's for the intercept. And then the second column is your x value. So if I wanted to predict the value of y at x equals 5, then x naught would be a vector, well, it's a 1 by 2 matrix. The first column is 1 and the second column is 5. Okay, so it would look like this. Okay, so just want to be really clear and understand, especially if you're new to matrices, you want to be very clear about your dimensions at all times. All right, so remember when we're constructing a prediction interval, we kind of look at the residuals, so y naught minus y naught hat. And y naught hat is just x naught times b, where b is our least squares estimator of beta. Okay? And we can show that the expected value of y naught minus y naught hat equals the expected value of y naught minus the expected value of x naught times b. The expected value of y naught, right? Y naught is just this guy. So let me go ahead and write that. X naught beta plus epsilon. And then x naught is not random, so I can pull it out of the expected value, right? The expected value of x naught times beta is just itself, since that's not random. The expected value of epsilon is 0 by our model assumption. So this equals x naught beta minus, and then I have the expected value of b is an unbiased estimator, so it's beta, and that is 0. Okay, so next we could show the variance of these residuals equals the variance of y naught minus, or plus, sorry, when you bring in a variance like that, it changes the sign to a positive, plus the variance of y hat naught, okay? This is the variance of x naught beta plus epsilon plus the variance, what is this? This is x naught b. Okay. This variance of this first piece of the term is 0 because this is a constant, so it zeroes out, and I'm left with just the variance of epsilon, which according to our model assumption is sigma squared times I. Okay, then I have over here, I have basically a constant times random. B is random, right? So I can pull this out as x naught variance of B times x naught transpose. Okay, so I have the sigma squared. Remember, this is going to be a scalar, so this I, it's just basically multiplied by 1. So I can go ahead and just drop it, plus x naught. Now, variance of B, we found this, right, in a previous video. This equals, let me go ahead and write it in a different color. So this equals sigma squared times x transpose x inverse. Okay, so that's the variance of B, and that's being multiplied by x naught transpose. So notice that this x is our observed design matrix. Okay. Notice sigma squared is in both terms, so I can go ahead and pull that out, and I'm left with 1 plus x naught x transpose x inverse times x naught transpose. Okay, and I always like to double check my dimensions when I get to the end, right? If I'm expecting a scalar, I should get a scalar. So what is x naught? The dimensions of x naught is a 1 by 2, if we have a simple linear regression model. What's the dimensions of x? X is an n by 2. So x transpose is a 2 by n. X naught transpose would be a 2 by 1. Okay, and we can see here that things cancel. So the n's cancel, the 2's cancel, and you're left with a 1 by 1. So that works. Good. That's what we were expecting. All right, and of course, this guy here, this variance, is not observed, where we don't know what the sigma squared, we don't know what the true model error is. So what we do is a lot of times we'll use the mean squared error, which is s squared, which is the sum of our squared residuals, or E transpose times E, divided by n minus 2. Okay, so once you plug this in, we stop going from a normal distribution to a t-distribution, right? And so now we're ready to go ahead and write our 1 minus alpha percent prediction interval. Okay. All right, so start with your estimate of the new value, right? So y naught hat, and then plus or minus, and we have the t-distribution, alpha divided by 2, n minus 2 degrees of freedom, and then times the estimate of this variance, so or actually, well, the square roots of the estimate of this variance. So the square root of s squared times 1 plus xo, x transpose x, inverse times xo transpose. Okay? And of course, you could pull out this s squared from the square root, and then it would just basically wouldn't be squared. So you could write this like s times the square root of all this jazz. All right, and there we have it. That is our 1 minus alpha prediction interval for a new response. So for YO, right? Y naught.